Bismillah ar-Rahman ar-Rahim. In this video, we will see how to characterize a PDK and generate lookup tables using ADT. I'm using the free PDK 45nm technology, and here I created a new library, and I will create a new schematic file, new cell view. I will get it from the taskbar. I will name it LUT gen tutorial. You can of course give it any name. Click OK. And now I need to instantiate the devices that I want to characterize. So I'll press I. This is my PDK, and these are the devices that I have. So I will instantiate the devices like this. Press F3 to get the window again. Get the second device, instantiate it in the schematic, and so on until you put all the devices that you want to characterize. So now I have instantiated all the devices. As we can see here, I have 4 NMOS transistors, 4 PMOS transistors. I have 2 thick oxide devices, and the remaining 6 are thin oxide devices, standard VT, high VT, and low VT. And I'm placing them a bit far away from each other because ADT will create actually stubs at each terminal. So the next step is to go to ADT menu here. Of course, you need ADT initialization script to be there in your .cds init file, which is in your Virtuoso project. And here I will generate LUT's netlist. You have 3 modes. The third one is what generates the valid values for the devices. What are the valid W's, what are the valid L's, and so on. So I will generate this mode, netlist and valid values full, and then it will ask me where I want to save the LUT's netlist that I'm going to generate. So I already have one file, I can overwrite it. I will just click save here. So I will replace my existing file, and it is asking me if I want to make it editable. Okay, I will click yes. And then I got a warning about the CDF mapping. So the CDF mapping is a very important step where you map the parameters of your PDK device to the generic ADT parameters, which are the width per finger, the number of fingers, the multiplier, the channel length, and so on. So every PDK has different naming for these parameters. So that's why it's important to do this CDF mapping. So I will click here CDF mapping, and this will open the CDF mapping form of ADT. So this is the CDF, or the device parameters mapping. By default, it selects the devices in the current cell only, and these are my 8 devices, as we can see here. So ADT tries initially to map the device parameters automatically, and if you find that the automatic mapping is not correct, you can edit it using this form. So as we can see here, the category is correct. It is MOSFET. Of course, if your device is FinFET, you can select it from here. And also we can see the PMOS devices are properly identified as PFET. The NMOS are NFET, so this is great. This is the length parameter. Of course, if you want to change it, you just need to double click here and choose any other parameter from the list, but it is already correct. And in this PDK, it is a bit strange because it doesn't have a width per finger and the number of fingers property. It just has the width and the multiplier. Of course, this is not the standard case for commercial PDKs. For commercial PDKs, you have finger widths, you have number of fingers. So here I will assume that the width parameter is actually the finger width. So I will Control C to copy this, and then select this part and press Control V. So here I selected the width parameter of the PDK as my finger width. I will just remove this from here, and the multiplier is the multiplier. The number of fingers is missing, so I will leave it blank. If I have a number of fingers property, I should select it from here, and if I have a total width property, which is basically the finger width times the number of fingers, I will also select it from here. But because I don't have a number of fingers property, I'll just leave this blank. The stack parameter is useful if you have a FinFET technology that allows you to stack devices vertically from the P cell, so you can also assign the stack parameter from here. So now I'm done with the CDF mapping step. I will press save, and ADT will add stubs, as we can see here, to the terminals of the device, and it will start generating the valid values. And the progress is shown here. I think it is done actually, and it says that the netlist is generated. Okay, I have my netlist already generated. If I want to edit the CDF mapping, you can also open it from the settings here, ADT settings, and then in the settings you will have the CDF mapping section, so you can click edit, and this will show you again the CDF mapping form if you want to make any edits. And if you want to know where these CDF mapping settings are saved, this gives you the output directory of ADT, and you can also open the CDF directory. It is the directory where the CDF mapping files are saved. So I'll just close this for now, and now I have my LUT's netlist ready. The next step is to go to ADT. I can open ADT here from the menu. I can click ADT GUI, or I can also go to the terminal and open ADT from the terminal. So this is my ADT work directory. It is an independent work directory. Usually better to use separate directories for ADT and for Virtuoso, not mixing them in the same directory. So I'll type ADT, press enter. Now ADT will load. I will choose the light mode, and then I will choose empty project. Okay, now I have an empty project of ADT. What I need to do is to browse for the netlist that I have generated from Virtuoso. So I will click browse. I will go and select my netlist. So this is the netlist file I have generated, and click open. So here I have my netlist file. So we can see that we have an error message here. It is complaining because ADT is expecting 4 parameters for every device. WN is the width, LN is the length, FN is the number of fingers, and MN is the multiplier. And we can see here for M0, for example, we have WN, LN, MN, but FN is missing because we don't have a number of fingers parameter for this PDK. So we just need to do a workaround. I will just multiply ADT MN by ADT FN. So as if we have an effective multiplier, that is the multiplication of the multiplier and the number of fingers. This is just a workaround so that we can have the 4 parameters defined. I will copy paste this to the other devices. These are the NMOS devices. For the PMOS devices, it is the same, but we need to replace the N with P. Of course, in commercial PDKs, you should have a parameter that is a number of fingers, so you don't need to do this workaround. Just copy this again to the other devices. And I think now I am done for all devices. I have 4 FN and I have 4 FP, all of them in the multiplier parameter. So I'll click save. This will save the netlist, and then now the netlist is parsed successfully. And I can see that the characterization table now, it has my devices, all my devices. The 8 devices are here. So we can make a device active or inactive. This will affect the generation process, so I can generate only some of them. And here I can check the parameters. Of course, the valid values were extracted automatically. So the valid L, for example, is from 50 nanos to 100 microns. But by default, ADT stops at 10 microns. You can edit this default if you want. And it picked the minimum correctly, which is the 50 nano. The parameter that you need to edit manually is the Vmax. The Vmax parameter is the maximum voltage that you want to characterize your device at, and this is not something that we can extract directly from the PDK, so you need to edit this manually. So I will set it to 1 volt here, press enter, and then I will apply this to all other devices. So now we can see this 1 volt is applied to all devices, but actually for the thick oxide device I can go up to 2 volts. So this is thick oxide. I'll change this to 2, and then I will go to the PMOS thick oxide device and also change this to 2. So Vmax is 1 for the thin oxide devices, Vmax is 2 for the thick oxide devices. When ADT characterizes the devices, it uses a reference width per finger and a reference number of fingers. So by default, these are 2 micron and 2 fingers. I will keep them as is. And then here comes the extraction method. The OP uses the DC operating point parameters. The BB is the black box characterization, which is more accurate. It takes a bit more time, but it is more accurate because it characterizes the effective parameters of the device. So I select BB for all of them. And then the accuracy, medium accuracy is usually recommended for production use, but when you start generation for the first time, it is best to start with test accuracy so that you make sure that everything is working fine. So I will apply this to other devices. So all of them will now use the test accuracy, and these are the parameters that I will characterize. If you open this output variables drop down, you will see that ADT characterizes the large signal currents, the OP, V threshold and V desat parameters, the AC parameters, and these AC parameters will be calculated as black box because we selected BB here, so we will get the effective GM, the effective GDS, the effective capacitance, and so on, the mismatch, and the noise. This includes the thermal noise and the flicker noise. So all of this get characterized for your devices. If my Virtuoso project was properly configured for the PDK, I would have expected to get my includes automatically here in the netlist, but this didn't happen for this free PDK, so I need to put the includes manually. If the includes were here, they will be parsed automatically and they will be populated in the include statements field. But this is not the case here, so I will just paste my include statement. So this is my include statement for the TT corner. Here you can change the temperature, or if you want to do it at multiple temperatures, you can actually use comma separated temperatures like this. I can do this to generate the TT corner for 3 temperatures. And if you want to add more corners, you need to click this plus button. So here I will add 2 more corners. This will be the name of the corner, and you can actually change the name if you want. So I will copy this include. The corner includes are the same. I'll just need to change this to SS and change this to FF. Of course, you need to check what are the include statements for your PDK, and if you have multiple include files, you can press Shift Enter and add the multiple files here. It is not a problem. So what I'm going to do is for TT, I will select temperature of 50. For SS, I will select temperature of 100. For FF, the fast, I will select the low temperature, 0. So this will give me an overall overview about my corner and temperature extremes. If you have mismatch models for your PDK, then you need actually to add the include statements for the Monte Carlo models here. This is something I don't have for this free PDK, so I will skip this step. But now I'm ready actually to start the generation. And these are the LUT file names. And if you are going to compare a PDK versus other PDKs, it is usually better to add here a prefix that indicates what is your PDK. So I can add this prefix, for example, so that I can differentiate between devices from different PDKs, because the LUT file name is the identifier that ADT uses to identify your LUT. So I'll keep this as is for now. And now I'm ready to generate LUTs. So I'll press generate LUTs. This will give me an estimate of the generation time and the size of the lookup tables. By default, we run parallel simulations for corners and temperatures, but we go device by device, and this is usually better because you finish one device, you save its LUT files, then you go for the other device, and so on. So we do it device by device. I'll click yes to continue. You will get a browse dialog to select where the LUTs are going to be saved. So you create a new directory for your lookup tables, and then you choose this directory, and the generation process will start. The generation process starts by doing device testing. Every device is tested to make sure that the included statements are correct, the parameters are correct, and everything is ready to do the generation process. So after the testing is done, of course I have a warning message here that the mismatch is missing, mismatch include is missing. So the mismatch generation will be skipped, but actually you can add the mismatch data later on. So you can have a lookup table without mismatch, and then when you have the mismatch model file, you can later add the mismatch information to the lookup table. So as we can see here, the corners of the first device are running in parallel. So here I have this device is characterized for the 3 corners I have specified and the 3 temperatures I have specified. After this device is done, it will go to the second one, and so on until the generation process is complete. So now the LUT generation process is complete. we can see here the process completed successfully and the files were saved in the path that we have chosen. And then we can load the lookup tables to use them in ADT, or just click no if we just want to save them on disk. So I will click yes here to load the lookup tables, and I will select all the lookup tables I have generated. I'll click open. So they are loaded successfully. I can reduce the size of this log tab now. Actually, if I checked this option, it will automatically load the LUTs after the generation process is complete. So these are test LUTs, so they are pretty small, and the purpose is just make sure everything is working fine. So I'll go now to the sizing assistant, and here I can choose my device and choose the criteria at which I want to plot my device properties. So here I'm sweeping the VGS, for example, setting fixed W, fixed L. So I can plot my drain current. So this is my drain current versus VGS. I can also do a parametric sweep. For example, I can use a comma here to plot at the min and the max L. So this is a parametric sweep. Of course, at the max L, the current is much smaller. I can define the width to be a ratio actually of L. So I have the same W over L ratio. Okay, so this looks more reasonable. So this is the 50 nano, this is the 10 micron characteristics using the same W over L. So this is a parametric sweep. Of course, you can plot any of the device properties, figures of merit, capacitances. This is the flicker noise, current referred, flicker noise, get referred, thermal noise, drain referred, thermal noise, get referred. And also let's compare the other devices. So I will just pick here the minimum L and plot the ID again. So this is the VTL device. I can go to the VTG device and click append here. So this is the VTG. The V threshold is higher, as you can see here. The VT high, so this is the high, or this is the PMOS one. So let's pick the VT high in MOS one. This is it. So I can append. So this is the VT high. You can see it here. And if I want to do a single point, for example, so select a GM over ID and fixed current. Okay, so now I have the device properties for this fixed point, the L, the W, all the properties here. For the small current, I got an error that the width is below the minimum width here. So I just increased my current, or of course I can increase my GM over ID to get a higher width. So these are the properties, the L, W, and everything. And if I want to do it at multiple corners, I can check the check boxes here to see how the device properties vary across corners. So these parameters are used to size the device at TT to get the L and W. And then the L and W are kept the same, and I see how the other parameters vary across corners. So I can see here the VGS varies, the GM over ID will vary as well, the FT will vary of course in the first corner it is much higher, and so on. So after you are satisfied with the initial results, you go back to the LUT generation tab, and now I change the accuracy to medium to generate the production lookup tables. Okay, so now I have medium in everything, and it is also best to store your settings. So here I can export the settings, and this will store all the LUT generation settings. So export settings, and for example I can name it FP45 LUT gen. This will be saved in a JSON file that I can reuse in the GUI, or actually use in the terminal to generate the lookup tables from the terminal. So now I have my settings exported. I can use it in other sessions by importing it, or I can use it also in the batch mode. This concludes our LUT generation tutorial. If you have any questions, please email us at support@master-micro.com, and we look forward to meeting you in future tutorials. Goodbye.